And now in this lecture we'll answer on two questions. In the first question we find out the area of this big circle, and in the second question we'll find out the area of this rectangle ABCD using two different methods. So we start with the first question. In the drawing we have two circles that touch each other at this point C. Point C is the point of tendency of the two circles with each other. In addition, we know that this is called CB, that is equal to 9 units in its length. This is called AC, that is equal to 16 units in its length. This is tangent DE, that is tangent to this small circle at point B, and tangent DE is tangent to this big circle at this point. So we'll define the point of tendency of tangent DE with this big circle. This point is point M. This is point B, and point B is considered as an external point in relation to this big circle. So from this common standpoint, point B, we have tangent BM, that is tangent to this big circle at point M. And in addition, from the same common standpoint, point B, if we draw this straight line, it will cut the big circle to points C and A. In this way, we create chord AC. And therefore, we can implement here rule 10. I'll pick rule 10. According to rule 10 is true in any circle. So in any circle, if from this common standpoint P, we will draw tangent PT, that is tangent to this circle at point C, and from the same common standpoint point P, you will draw this straight line in such a way that you will create here chord AB. Then in this drawing, the following equation is true, that PT square equals to PA times PB. Again, PT square equals to PA times PB. We can definitely implement rule 10 in our drawing. Why? Because in our drawing, from this common standpoint point B, we have tangent BM, that is tangent to this big circle at point M. In addition, from the same common standpoint B, if we draw this straight line, it will cut the big circle at 2 points, point C and point A. Therefore, we can create chord AC. So all the requirements of rule 10 are satisfied, and therefore, according to rule 10, the following equation is true, that BM square equals to BC times BA. Again, BM square equals to BC times BA. So I will write it down. So according to rule 10, BM squared equals to BC times BA. Repeat again, according to rule 10, BM squared equals to BC times BA. BM is the missing tangent, so we leave it as it is, so it is BM squared. That is equal to BC. BC is 9 times BA. BA in total is 9 plus 16, that is 25. So BA is 25. So in total, we found out that according to rule 10, BM squared equals to 9 times 25. Here we take a root out of this equation, and we get that BM equals to the square root of 9, that is 3, times the square root of 25, that is 5. So in total, BM equals to 3 times 5, that is 15. So the length of tangent BM is equal to 15 units. So this is tangent BM, the length of this tangent BM is 15 units. In the next step, we will do a construction. That is to say, from this point C, we do a common tangent that belongs to both circles. That is to say, the tangent that we will draw, it will be tangent to this small circle point C, and the same common tangent also will be tangent to this big circle. And we define the touching point of the common tangent at point C. So we define the common tangent that we drew. We define the touching point of the common tangent with tangent DE. This point is point N. I repeat again that tangent NC is a common tangent that belongs to both circles. Tangent NC is tangent to this small circle at point C, and it is also tangent to this big circle at the same point, point C. So point C is a common tangent that belongs to both. So tangent NC is a common tangent that belongs to both circles. In the next step, we will focus on this common external point, point N. For this common external point N, we have two tangents to the small circle, tangent NC and tangent NB. And according to rule 2, they are equal to each other. That is to say, NC equals to NB. So I'll repeat quickly on rule 2. According to rule 2, the lengths of two tangents from a common external point to a circle are equal. So in the drawing, we have a circle, and this is the common external point, point P. From this common external point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, PA equals to PB. We can definitely implement rule 2 as already done already. From this common external point, point N, we have two tangents to this small circle, tangent NC and tangent NB. And according to rule 2, they are equal to each other. That is to say, NC equals to NB. In the next step, I'll copy triangle C and B in a new page, and we will analyze this triangle C and B. So here, this is triangle C and B that I got from the original drawing. In this triangle C and B, side CN equals to side NB according to rule 2. And we have also the rule that states that in front of equal sides in the triangle there are equal angles. So in front of this side CN we have this angle, this is actually angle CBN, and in front of this side NB we have this angle, that is actually NCB. And because of the fact that those two angles are located in front of those two equal sides, they must be also equal to each other in their sizes. So if the size of this angle is alpha, then the size of this angle must be also equal to alpha, because they are equal to each other according to the rule that I mentioned. So in total, I actually found out that this is angle NCB that is equal to alpha, and angle NBC also equals to alpha. So actually, angle NCB equals to alpha, and angle CBN also equals to alpha. In the next step, we join point C and M together by a straight line. And we will continue to focus on this common external point, point N. For this common external point, point N, we have two tangents to this big circle, tangent NC and tangent NM. And according to rule 2, they are equal to each other. That is to say, NC equals to NM. So in the next step, I'll copy the triangle C and M in the new page, and we will analyze this triangle C and M. So actually this is triangle CMM that I call it from the original drawing. In this triangle CNM, side CN equals to side NM according to rule 2. And in front of side CN we have this angle that is actually angle CMN, and in front of this side MN, in front of this side MN we have this angle that is actually angle NMCN. And because of the fact that those two angles are located in front of those two equal sides, they must be also equal to each other in their sizes. So if the size of this angle is beta, then the size of this angle must be also equal to beta because they are equal to each other. So in total we found out that angle MCN equals to beta. This is angle MCN that is equal to beta, and angle CMN also equals to beta. This is angle CMN that is equal to beta. In the next step, I'll copy the big triangle MCB in the new page, and we'll analyze this triangle MCB. Okay, this is triangle MCB that I call it from the original drawing. In this triangle MCB, the sum of the angles must be equal to 180 degrees. It is true in any triangle, especially it is true in this triangle MCB. So which angles we have in triangle MCB? We have this angle that is alpha, plus this angle beta, plus the big angle that is beta plus alpha. In total, the sum of those two angles must be equal to 180 degrees according to the rule that I mentioned. So, in this side of the equation, we have alpha plus alpha, that is 2 alpha, beta plus beta is 2 beta, so 2 alpha plus 2 beta equals to 180 degrees according to the rule that I mentioned. Here we divide this equation by 2, and finally we get that alpha plus beta equals to 180 degrees over 2 is 90 degrees. So we found out that the big angle MCB is equal to 90 degrees in its side, so it is a right angle. So actually, this is the big angle. This is the big angle MCB, that is a right angle. It is given us in the question that AB is a straight line. If we focus on the left side of the straight line AB at point C, here the sum of the angles must be equal to 180 degrees according to rule 3 that says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the left side of the straight line AB at point C? We have this angle that is a right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees. Therefore, this missing angle must be equal to 90 degrees in its size. Sorry, angle ACM is a right angle. Angle ACM is located inside the big circle, and therefore angle ACM is defined as a peripheral angle. So inside the big circle we have a peripheral angle that is equal to 90 degrees in its size. In the next step we join points A and M together by a straight line. By joining points A and M, we created a chord AM. Chord AM is a chord inside this big circle. And angle ACM is a peripheral angle. The size of this peripheral angle ACM is 90 degrees. So here we can implement rule 5. So I'll take rule 5. According to rule 5, any peripheral angle that is equal to 90 degrees must subtend on the diameter of the circle. So here we have a circle. This point we have a circle. This is a circle, and this is peripheral angle MAN. And we know that peripheral angle MAN is a right angle. That is to say, it is equal to 90 degrees in its size. And therefore, according to this rule 5, peripheral angle MAN must subtend on the diameter of the circle. And because of the fact that peripheral angle MAN subtend on MN, MN must be the diameter of the circle, according to this rule 5. So whenever you have a peripheral angle that is a right angle, it must subtend on the diameter of the circle. So we can implement rule 5 in our drawing. Well, because in our drawing, we have peripheral angle ACM, that is a right angle, and according to rule 5, any peripheral angle that is equal to 90 degrees in its size must subtend on the diameter of the circle. And because of the fact that peripheral angle ACM, that is a right angle, subtend on AM, we conclude that according to rule 5, AM must be the diameter of this big circle. So I write it down. According to rule 5, chord AM is the diameter of the big circle. Chord AM is the diameter of the big circle. We also know that the center of any circle must be located on the diameter of the circle. Again, the center of any circle must be located on the diameter of the circle. And because of the fact that AM is the diameter of this big circle, the center of this big circle must be located on AM. So here, this is the center of this big circle. We define the center of this big circle as O. Point O is definitely located on AM, that is the diameter of this big circle. So point O is the center of this circle, point M is the point of this big circle itself, therefore OM is the radius of this big circle. We define the radius of this big circle as R, so OM equals to R, according to our definition. And because of the fact that the radius OM that is equal to R, the radius OM is drawn to point M, that is the point of tendency of tangent DE with this big circle, and whenever your radius that is drawn to the point of tendency, then tangent DE will be perpendicular to the radius MO. If D is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So in the next step, I'll copy the right big triangle A and B in the new page, and we'll implement the Pythagoras theorem in this right triangle A and B. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in this right triangle A and B is AB, and the length of the hypotenuse AB in total it is 16 plus 9, that is 25. Side AM is unknown, is the missing side, and the length of side A and B is 15 units according to rule 10. So I copy this side triangle A and B, and we implement the Pythagoras theorem in this side triangle A and B. So actually, this is the right triangle A and B that are coming from the original drawing. This triangle A and B, according to the Pythagoras theorem, AB squared, that is the square of the hypotenuse, is equal to AM squared plus MB squared. So in the right triangle A and B, according to the Pythagoras theorem, AB squared equals to AM squared plus MB squared. The hypotenuse AB is 25, therefore AB squared is 25 squared, that is 625. And it is equal to AM squared. AM is the missing side, so we limit as it is, so it is AM squared plus MB squared. MB is 15, therefore MB squared is 15 squared, this is 225. So in total we found out that according to the Pythagoras theorem, the right triangle A and B, 625 equals to AM squared plus 225. Here we subtract 225 from this equation, and we get that 625 minus 225 is 400, so 400 equals to AM squared. Here we take a root out of this equation, and finally get that the missing side AM is equal to the square root of 400, that is 20. So, this is the missing side AM that is equal to 20 units in its length. But we already found out that according to rule 5, chord AM is the diameter of the big circle. Chord AM is the diameter of this big circle. So the diameter AM over 2 is equal to the radius R. Again, the diameter AM of the big circle over 2 is equal to the radius R. So the radius R equals to AM, that is 20 over 2 is 10. So the radius R of this big circle is equal to 10 units in its length. Our mission is to find out the area of this big circle. So actually we know that the area of any circle is equal to pi times the radius of the circle squared. Therefore, the area of the big circle must be equal to pi times the radius of the big circle squared. The radius of the big circle is 10, therefore the radius squared is 10 square. So in total, the area of the big circle must be equal to pi times 10 square. 10 square is 100. So in total, this expression equals to 100 pi. So if you found out the area that we are looking for this question, that is the area of the big circle, equals to either 100 pi, or in terms of numbers, it is equal to 314.159 square units. And that is the answer to the first question. Okay, again, if we found out that the area of this big circle equals to either 100 pi, in terms of numbers, the area of this circle equals to 314.159 square units. So we finish with the first question. In the next step, I will present you the second question, and we will solve the second question in two different methods. Our mission in the second question is to find out the area of this rectangle ABCD. So in the moment we have rectangle ABCD and we have also this semicircle. It is given as the question that the length of chord AM is 5 units. Again, our mission is to find out the area of this rectangle ABCD. So we'll start with the first method. First of all, because of the fact that ABCD is a rectangle, all those four angles inside rectangle ABCD are right angles. So this is a right angle. This is also a right angle. This is a right angle. And this is also a right angle. In the next step, we define the center of this semicircle. This point is point O. We define the radius of this semicircle as x. So point O is the center of this semicircle, point A is the point of the semicircle itself. So this is exactly the definition of a radius. Therefore, OA is the radius of this semicircle that is equal to x unit in its length according to our definition. In the next step, we define the point of tendency of this ended DC with this circle. This point is point E. And we join points O and D together by a straight line. And again, we join points O and E together by a straight line. What is the definition of line segment OE? Line segment OE starts from point O, that is the center of the semicircle, and then at point E, that is the point of the semicircle itself. So this is exactly the definition of a radius. Therefore, OE is the radius of this semicircle. It is equal to x units in its length according to our definition. Because of the fact that the radius OE that is equal to x, the radius OE is drawn to point E, that is the point of tendency of tangent DC with this semicircle, and whenever we have a radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius EO. If DC is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So inside quadrilateral DEOA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral DEOA we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be at least a rectangle in flat square. So we relate to this quadrilateral DEOA as a rectangle because it has 4 right angles. So quadrilateral DEOA is a rectangle according to rule 5. But we also know that the opposite sides of an octagon are equal to each other. So in octagon EOAD, side EO must be equal to the opposite side DA, but EO is x, therefore DA must be also equal to x units in its length. In the next step, we define this line segment OB as A, and we define this line segment MB as B. And we join points O and M together by a straight line. What is the definition of line segment OM? Line segment OM starts from point O, that is the center of the semicircle, and ends at point M, that is the point of the semicircle itself. So this is exactly the definition of a radius. Therefore, OM is the radius of this semicircle that is equal to x units in its length according to our definition. So in the next step, I'll copy the right triangle OMB in a new page, and we will implement the Pythagoras theorem on this right triangle OMB. Here by PT is the relation for Pythagoras theorem. So actually, this is the right triangle OMB that I copied from the original drawing. This right triangle OMB, M all squared, that is the square of the hypotenuse, equals to MB squared plus B all squared. So I write it down. M all squared, that is the square of the hypotenuse, is equal to MB squared plus OB squared. This is equation 1. MO equals to x, it is the radius of the semicircle, so MO squared is x squared, and it is equal to MB squared. MB is B, therefore MB squared is B squared plus BO squared. BO is A, therefore BO squared is A squared. So in total, according to equation 1, we actually found out that x squared equals to B squared plus A squared. In the next step, I'll copy this right triangle A and B in a new page, and we will implement the Pythagoras theorem on this right big triangle, triangle A and B. So here by PT is the relation for Pythagoras theorem. The hypotenuse AM equals to 5 units in its length, according to what is given as the question. Side AB of the right triangle AB equals to x plus A. And side AB equals to B units in its length, according to our definition. So actually, this is the right triangle AMB that is covered from the original drawing. This right triangle AMB, MA square, that is the square of the hypotenuse, equals to MB square plus BA square. So I write it down. This will be equation 2. MA squared, that is the square of the hypotenuse, is equal to MB square plus BA square. The hypotenuse MA is 5, therefore MA square is 5 squared, that is 25, and it is equal to MB square. MB is B, therefore MB square is B square plus BA square. BA is x plus a, therefore BA square is x plus a square. So in total, according to equation 2, we should find out that 25 equals to B square plus x plus a square. So 25 equals to B square plus x plus a square. X plus a square equals to x square plus a square plus 2 times x times a. So in the right side of this equation 2, we have the expression b square plus a square. But b square plus a square, according to equation 1, b square plus a square is equal to x square. Therefore, we substitute b square plus a square in this equation 2, by x square from equation 1. We'll do it now, and we'll get that according to equation 2, 25 equals to b square plus a square is x square, plus x square again, plus 2xa. So in total, according to equation 2, we actually found out that $25 equals to x square plus 2xa. So 25 equals to x square plus x square is 2x square plus 2xa. Here we divide this equation 2 by 2, and we get that 25 over 2 is 12.5. So 12.5 equals to 2x square over 2 is x square. 2xa over 2 is xa. So in total, according to equation 2, we can find out that 12.5 equals to x square plus xa. So 12.5 equals to x square plus xa. So here we take out x as a common factor. So x was taken out as a common factor from those two expressions. So what is left from x square after we commit x as a common factor? What is left is actually x. Plus what is left from xa after we commit x as a common factor? What is left is actually a. So in total, according to equation 2, we actually found out that 12.5 equals to x times x plus a. Our mission is to find out the area of this rectangle ABCD. So what is the area of rectangle ABCD? Actually, we know that the area of any rectangle equals to the length of the rectangle times the width. And therefore, the area of rectangle ABCD must be equal to the length of the rectangle ABCD times the width. What is the length of rectangle ABCD? The length of this rectangle ABCD is AB. Times the width. The width is dA. So in total, we found out that the area that we are looking for in this question, that is the area of rectangle ABCD, it is equal to AB times dA. AB is x plus a, and dA is x. So in total, we found out that the area of rectangle ABCD equals to x plus a times x. But according to this equation, equation 2, x plus a times x is 12.5. Therefore, we can substitute x plus a times x by 12.5. So in total, we found out that the area of rectangle ABCD is equal to 12.5 square units. And this is the answer to the question. I'll repeat again. We actually found out that the area of this rectangle ABCD is equal to 12.5 square units. So we finish with the first method. In the next step, I will present to you how to find out the area of this rectangle ABCD according to the second method. So first of all, because of the fact that ABCD is a rectangle, all of its four angles are right angles. So those four angles are right angles. So this is a right angle. This is also a right angle. This is a right angle. And finally, this is a right angle. We define the center of this semicircle. This point is point O. We define the radius of this semicircle as x, exactly as we did in the first method. So point O is the center of the semicircle, point A is the point of the semicircle itself, therefore OA is the radius of the semicircle that is equal to x units in its length according to our definition. We have already found out in the first method that dA equals to x units in its length, so I will not repeat on the same explanation. dA equals to x units in its length according to the first method. In the next step, we define this line segment OB as A. We define this point as N. In the next step, we join points M and N together by a straight line. By joining points M and N, we get the peripheral angle AMN. Peripheral angle MAN subtend on AN. And AN is the diameter of this semicircle, and according to rule 7, any peripheral angle that subtend on the diameter of the circle or semicircle must be equal to 90 degrees in its size. And therefore this peripheral angle AMN must be equal to 90 degrees in its size. So, I'll repeat quickly on rule 7. According to rule 7, if the peripheral angle subtend on the diameter of the circle, then it is equal to 90 degrees. So in the drawing we have a circle, and we know that AB is the diameter of this circle. We also have here peripheral angle ACB. Peripheral angle ACB subtend on AB, that is the diameter of this circle, and therefore according to this rule 7, peripheral angle ACB must be equal to 90 degrees in its size. Why? Because of the fact that it subtend on AB, that is the diameter of this circle. So any peripheral angle that subtend on the diameter of the circle must be equal to 90 degrees in its size. We have already implemented rule 7 in our drawing. Why? Because we have here peripheral angle AMN that is subtend on AN, that is the diameter of this semicircle, and therefore according to rule 7, peripheral angle MAN must be equal to 90 degrees in its size. Okay. In the next step, we'll define this angle as angle alpha. So in the right triangle AMN, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, We focus on this right angle A and B. This right angle A and B, this angle equals to alpha, this angle equals to 90 degrees, and therefore, again, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees. Now, alpha, according to the sum rule, that states that the sum of the angles in any triangle is equal to 180 degrees. It is very easy to see that this is angle A, that is a common angle that belongs to both triangles. Angle A belongs to the right triangle MAB, and angle A also belongs to the right triangle NMA. So angle A is a common angle that belongs to both triangles. So in the next step, I'll copy the right triangle A and B and the right triangle AMN in an equation. We'll prove that those two right triangles are similar to each other according to angle similarity rule. Side AM equals to 5 units in its length. This is side AB of the right triangle AMB. In total, side AB equals to x plus a. This is line segment AN, that is the diameter of this semicircle. The radius of this semicircle is x, therefore the diameter is twice as long as the radius. So if the radius is x, the diameter must be equal to 2x. So AN equals to 2x units in its length. So here those are the two right triangles. This is triangle AMB. So those are the two right triangles, triangle AMB and triangle AMN, that are coming from the original drawing. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees and therefore they are equal to each other. So actually this is angle ABM. In the right triangle AMB, and it is equal to this angle, that is actually angle AMN. In the right triangle AMN, they are both equal to 90 degrees and therefore they are equal to each other. In addition, as I already mentioned before, This is angle A, this is a common angle that belongs to both triangles. Angle A belongs also to triangle AMN, as you can see here. So angle A equals to itself is a common angle that belongs to both triangles. So if we relate to angle A, since it belongs to the right triangle A and B, it will be defined as angle MAB. And angle A equals to itself, so if we relate to angle A, since it belongs to this triangle AMN, it will be defined as angle MAN. Angle A equals to itself is a common angle that belongs to both triangles. This equation means that angle A equals to itself. It's just called to angle A two different names. Angle A equals to itself is a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually this is angle A and B. In the right triangle A and B, it is equal to this angle, that is actually angle A and M. In the right triangle AMN. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we actually prove that all the triangles of this right triangle A and B are correspondingly equal to all the triangles of this right triangle AMN, and therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. Triangle A and B is similar, this is the sign of similar, to the right triangle AMN according to angle similarity rule. And for the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AM of this right triangle A and B over side AN of this right triangle AMN is equal to side AB of this right triangle A and B over side AM of this right triangle AMN. So I repeat again. We will derive that side AM of the right triangle A and B over side AN of the right triangle AMN equals to side AB of the right triangle A and B over side AM of the right triangle AMN. AM is 5 according to what is given as the question. We have already shown to you that AN is the diameter of the semicircle, therefore it is equal to 2x because the radius is x. AB is x plus a over AM, that is 5. So in total, according to equation 1, we actually found out that 5 over 2x equals to x plus a over 5. Here we first multiply this equation, equation 1, and finally get that 5 times 5 is 25, and it is equal to 2x times x plus a. So here we divide this equation 1 by 2, and finally get that 25 over 2 is 12.5, and it is equal to 2x over 2 is x, so in total this expression equals to x plus x times x plus a. So in total, according to equation 1, we actually found out that 12.5 equals to x times x plus a. Our mission is to find out the area of this rectangle ABCD. So what is the area of rectangle ABCD? Actually, we know that the area of any rectangle equals to the length of the rectangle times the width. repeat again, the area of a rectangle equals to the length of the rectangle times the width. And therefore, the area of rectangle ABCD must be equal to the area of the length of the rectangle ABCD times the width. The length of this rectangle ABCD equals to AB, and the width is DA. So in total, we can find out that the area of rectangle ABCD equals to AB times DA. AB is x plus A, and DA is x. So in total, the area of rectangle ABCD equals to x plus A times x. But according to equation 1, x plus A times x is 12.5. Therefore, we can substitute x plus A times x here by 12.5. We do it now and we get actually that in total the area of rectangle ABCD is equal to 12.5 square units. So actually in both methods we found out that the area that we are looking for this question, that is the area of this rectangle ABCD, is equal to 12.5 square units. We finished with the second question, so in the next step I'll summarize the lecture. We'll start with the first question, of course. So our mission, the first question is to find out the area of this big circle. So in the drawing we have two circles that touch each other at this point C. In addition, we know that this is called AC, that is equal to 16 units in its length. This is called CV, that is equal to 9 units in its length. This is tangent DB, this is tangent DE, that is tangent to this small circle at point B here, and tangent DE is tangent to this big circle at this point M. So first of all, we know that point B is considered as an external point in relation to this big circle. So from the common external point B, we have a tangent BM that is tangent to this big circle at this point M. In addition, from the same common external point B, we have here, if we draw this straight line, it will cut the big circle 2 points, C and A. This way created here called AC. So all the requirements of Rule 10 are satisfied, and therefore we can implement here Rule 10. According to Rule 10, the following equation is told that BM square equals to BC times BA. Again, BM square equals to BC times BA. So repeat again. In the current standpoint point B, according to Rule 10, the following equation is told that BM square equals to BC times BA. BM is the missing tangent, so we leave it as it is. So BM square equals to BC. BC is 9 times BA. BA in total is 9 plus 16, that is 25. So BA is 25. So again, BC is 9 and BA is 25. So in total we shall find out that BM square equals to 9 times 25. So here we talk about the equation and finally found out that BM equals to the square root of 9, that is 3, times the square root of 25, that is 5. So in total, BM equals to 3 times 5, that is 15. So the length of this tangent BM is 15 units. In the next step, we did a construction, that is to say, from this point C, we drew tangent, that is a common tangent to these circles. So, and we defined the touching point of the common tangent from point C and DE. This point is point N. So actually, NC is a common tangent that belongs to both circles. NC is a tangent to this small circle, point C, and NC is also a tangent to this big circle, and the same point is point C. So point C is a common tangent. So NC is a common tangent that belongs to both triangles, to both circles. Okay, so in the next step, we focus on this common standpoint, point N. From this common standpoint, point N, we have two tangents to this small circle, tangent NB and tangent NC. The following two, they are equal to each other. That is to say, NC equals to NB. So in the next step, I copy triangle NCB. In your page, and analyze this triangle, triangle CNB. So this is triangle CNB that according to the original drawing, according to rule 2, side CN equals to side NB. And according to the rule that states that in front of equal sides in the triangle there are equal angles, we get that in front of this side CN we have this angle, in front of this side NB we have this angle. And because of the fact that those two angles are located in front of those two equal sides, they must be also equal to each other and their sizes. So if the size of this angle is alpha, then the size of this angle must be equal to alpha according to the rule that I mentioned. So in total, we shall find out that angle NCB equals to alpha, and angle NBC also equals to alpha. So this is angle NCB that is equal to alpha, and this is angle CBN that is also equals to alpha. In the next step, we join point C and M together by straight line. And we continue to focus on this common standpoint, point N. From this common standpoint, point N, we have two tangents to this big circle, tangent NC and tangent NM. And according to rule 2, they are equal to each other. That is to say, NC equals to NM. So in the next step, I call this triangle CMN. In the page, we analyze this triangle, triangle CMN. This is triangle CMN that I call it from the original drawing. According to rule 2, side CN equals to side NM. In front of this side CN, we have this angle, that is angle CMB. In front of this side MN, we have this angle, that is actually angle MCN. And because of the fact that those two angles are located in front of those two equal sides, they must be also equal to each other and their sizes. So if the size of this angle is better, then the size of this angle must be also equal to beta, because they are equal to each other according to the rule that I mentioned. So in total, we found out that angle MCN equals to beta and angle CMN also equals to beta. This is angle MCN that is equal to beta, and this is angle CMN that is also equal to beta. In the next step, I copied the big triangle MCB in a new page. We analyze this big triangle, triangle MCB. So actually, this is triangle MCB that I call it from the original drawing. In this triangle MCB, the sum of the angles must be equal to 180 degrees. It is true in any triangle, and especially it is true in this triangle, triangle MCB. So each angle we have in triangle MCB, we have this angle that is alpha plus this angle that is beta plus this angle that is beta plus alpha. In total, the sum of those three angles must be equal to 180 degrees. So in this side of the equation, we have alpha plus alpha, that is 2 alpha. Beta plus beta is 2 beta, so in total 2 alpha plus 2 beta equals to 180 degrees. Here we divided this equation by 2 and finally found out that alpha plus beta equals to 180 degrees over 2 is 90 degrees. So the big angle MCB is equal to 90 degrees in its size. That is to say, it is a right angle. So okay, this is the big angle MCB, that is a right angle. It is given as a question that AB is a straight line. So if we focus on the left side of the straight line AB, it's point C here. So here the sum of the angles must be equal to 180 degrees according to rule 3 that says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the left side of AC at point C, we have this angle that is a right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we join points A and M together by a straight line. Or AM is a chord inside this big circle. And we have also here peripheral angle ACM. And according to rule 3, peripheral angle ACM is a right angle. So inside this big circle, we have peripheral angle that is a right angle. And according to rule 5, any peripheral angle that is equal to 90 degrees in its size, that is to say it is a right angle, must subtend on the diameter of the circle. And because of the fact that peripheral angle ACM that is a right angle subtend on AM, AM must be equal to the diameter of this big circle according to rule 5. So AM is the diameter of this big circle according to rule 5. Here, according to rule 5, chord AM is the diameter of the big circle. We know that the center of any circle must be located on the diameter of the circle. Again, the center of any circle must be located on the diameter of the circle. So, because of the fact that AM is the diameter of this big circle, the center of this big circle must be located on AM. So here, this is the center of this big circle that is definitely located on the diameter AM. So point O is the center of this big circle. Point M is the point on the big circle itself. Therefore, OM is the radius of this big circle. We define the radius of this big circle as R. So OM equals to R, and because of the fact that the radius OM that is equal to R, the radius OM is drawn to point M, that is the point of tendency of tangent DE with this big circle, and whenever you have a radius that is drawn to the point of tendency, then tangent DE will be perpendicular to the radius MO. If D is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, I copied the right big triangle A and B in Olympiad and implemented the Pythagoras theorem in this right triangle, triangle A and B. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in this right triangle A and B is AB. AB in total is 16 plus 9, that is 25. AM is the missing side, MB is 15 units in its length according to rule 10. So actually, this is the right triangle A and B that are coming from the original domain. In this right triangle A and B, AB square, that is the square of the hypotenuse, must be equal to AM square plus MB square. AB square equals to AM square plus MB square according to the Pythagoras theorem. AB is 25, therefore AB square is 25 square, that is 625, and it is equal to AM square. AM is the missing side, so we leave it as it is, plus BM square. BM is 15, therefore BM square is 15 square, that is 225. So in total, if we found out that 625 equals to AM square plus 225. Here we subtracted 225 from this equation, and finally found out that 625 minus 225 is 400. So 400 equals to AM square. Here we took a root out of this equation, and finally found out that the missing side AM equals to the square root of 400, that is 20. So AM equals to 20 units in its length. But we already found out that according to rule 5, AM is the diameter of the big circle. So if AM is the diameter of this big circle, so AM equals to 20 units in its length. If the diameter is 20, the radius must be equal to half of it. So the radius of this big circle R must be equal to 20 over 2, that is 10. Repeat again. The radius R of the big circle must be equal to half of the diameter. That is to say, to AM over 2. AM is 20, so 20 over 2 is 10. So the radius of the big circle is equal to 10 units in its length. Our mission is to find out the area of this big circle. Actually, we know that the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of the big circle must be equal to pi times the radius of the big circle, that is 10 squared. So in total, the area of the big circle must be equal to pi times 10 squared. 10 squared is 100, so in total this expression equals to 100 pi. 100 pi is 314.159. So in total we found out the area of this big circle equals to either 100 pi square units, so in terms of numbers, the area of this big circle equals to 314.159 square units. We finished with the first question. In the next step, I presented to you the second question, and we solved the second question in two different methods. Our mission in the second question is to find out the area of this rectangle ABCD. So we start with the first method. In the drawing we have rectangle ABCD and we have this semicircle. In addition, we know that this is 970 AM, that is equal to 5 units in its length. Again, our mission is to find out the area of this rectangle ABCD. Because of the fact that ABCD is a rectangle, all the angles inside the rectangle ABCD are right angles, so all those four angles are right angles. In the next step, we defined the radius of this semicircle as O. This is the radius of this semicircle, this is O. According to our definition, we defined the center of this semicircle. This point is point O. We defined the radius of this semicircle as X. Point O is the center of the semicircle, point A is the point of the semicircle itself, therefore OA is the radius of the semicircle, that is equal to X units in its length according to our definition. We define the point of tendency of tangent DC, this tangent DC which the semicircle, this point is point E. In the next step we join points O and E together by straight line. Point O is the center of the semicircle, point E is the point of the semicircle itself, therefore OE is the radius of the semicircle, that is equal to X units in its length according to our definition. Because of the fact that the radius OE that is equal to X, the radius OE is drawn to point E, that is the point of tendency of tangent DC with this semicircle, and whenever you have a radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius EO. If this is perpendicular to the O, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So, inside quadrant DEOA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the side of this 4th angle, in total it must be equal to 360 degrees according to the rule that states then the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this 4th angle must be equal to 90 degrees in its size. So inside quadrilateral ADEO we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be this right angle flat as square. So we will relate to quadrilateral ADEO as a right angle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ADEO, side EO must be equal to the opposite side DA, but EO is X, therefore DA must be also equal to X units in its length. In the next step, we define this line segment OB as A, and this line segment BM as B. We join points O and M together by straight line. Point O is the center of the semicircle, point M is the point of the semicircle itself, so this is exactly the definition of a radius. Therefore, OM is the radius of this semicircle, that is equal to X units. In the next step, I copied the right triangle OMB in a new page and implemented the Pythagoras theorem on this right triangle, triangle OMB. Okay, this is the right triangle OMB that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle OMB, MO square equals to MB square plus BO square. MO is X, therefore MO square is X square. And it is equal to MB square. MB is B, therefore MB square is B square plus BO square. BO is A, therefore BO square is A square. So in total, according to equation 1, X square equals to V square plus A square. In the next step, I copied the right big triangle A and B in a new page and implemented the Pythagoras theorem on this right big triangle A and B. This is the right triangle A and B, the right big triangle A and B that I copied from the original drawing. The hypotenuse AM is 5 units. According to what is given in the question, MB is B according to our definition, and side AB in total equals to x plus a. So in this side, right triangle A and B, according to the Pythagoras theorem, AM square equals to MB square plus BA square. AM is 5, therefore AM square is 5 squared, that is 25, and it is equal to MB square. MB is B, therefore MB square is B square, plus BA square. BA is x plus a, therefore BA square is x plus a square. So in total according to equation 2, we shall find out that 25 equals to B square plus x plus a square. So 25 equals to B square plus x plus a square. X plus a square equals to x square plus a square plus 2 times xa. So in this side of equation 2, we have the expression b square plus a square. But according to equation 1, b square plus a square equals to x square. Therefore, we can substitute b square plus a square by x square from equation 1. We did it, and we shall find out that according to equation 2, equals to b square plus a square is x square, and we have x square again, plus 2xa. X square plus x square is 2x square, so 25 equals to 2x square plus 2xa. Here we divided this equation 2 by 2, and finally found out that 25 over 2 is 12.5, 2x square over 2 is x square, and 2xa over 2 is xa. So in total, according to equation 2, we shall find out that 12.5 equals to x square plus xa. Here we took x as a common factor out of those two expressions. So 12.5 equals to x was taken out as a common factor from those two expressions. So what is left from x square after we took from it x as a common factor? What is left is actually x. What is left from xa after we took from it x as a common factor? What is left is actually a. So in total, according to equation 2, we shall find out that 12.5 equals to x times x plus a. Our mission is to find out the area of this rectangle ABCD. So we know that the area of any rectangle equals to the length of the rectangle times the width. And therefore the area of this rectangle ABCD must be equal to the length of the rectangle ABCD times the width. The length of this rectangle ABCD is AB, and the width is DA. Again, the length is AB and the width is DA. So in total, the area of rectangle ABCD must be equal to AB times DA. AB is x plus a, and DA is x. Again, AB is x plus a, and DA is x. So in total, we shall find out that the area of rectangle ABCD equals to x plus a times x. But according to equation 2, x plus a times x is 12.5. Therefore, we can substitute x plus a times x by 12.5. We did it, and in total we found out that the area that we are looking for this question, that is the area of rectangle ABCD, is equal to 12.5 square units. We finished with the first method. In the next step, I presented to you how to find out the area of this rectangle ABCD according to the second method. So first of all, because of the fact that ABCD is a rectangle, all those triangles inside rectangle ABCD are right angles. We define the center of this semicircle as O. We define the radius of this semicircle as x. OA is the radius of this semicircle, that is equal to x. We define this line segment OB as A. We define this point as point M. In the next step, we join points M and N together by a straight line. By joining points A and M and N, we created the peripheral AMN. This is peripheral AMN that subtends on AN. AN is the diameter of the semicircle, and according to rule 7, any peripheral angle that subtends on the diameter of the semicircle or circle or semicircle must be equal to 90 degrees in its size. Therefore, according to rule 7, because of the fact that peripheral angle AMN subtend on AN, that is the diameter of this semicircle, it must be equal to 90 degrees in its size. Okay. In the next step, we define this angle as alpha. So in the right triangle AMN, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the right triangle A and B, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this premise, again, this angle equals to alpha, this angle equals to 90 degrees, and therefore this premise again must be equal to 90 degrees minus alpha. Okay. This is angle A, that is a common angle that belongs to both triangles. Angle A belongs to the right triangle A and B, and angle A belongs also to the right triangle A and N. So angle A is a common angle that belongs to both triangles. In the next step, I complete the right triangle A and B and the right triangle A and N in an equation. We prove that those two right triangles are similar to each other according to angle similarity rule. So actually, those are the two right triangles A and B and A and N that are going from the original drawing. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees and therefore they are equal to each other. In addition, as I already mentioned before, angle A is a common angle that belongs to both triangles. So we can write down that angle A equals to itself as a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we shall prove that all the figures of the right triangle A and B are correspondingly equal to all the figures of this right triangle A and N, and therefore those two right triangles are similar to each other according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive the side AM of this right triangle A and B, or side AN of this right triangle A and N, equals to side AB of this right triangle A and B, or side AN of this right triangle A and N. So repeat again. We will derive that side AM of the right triangle A and B over side AN of the right triangle A and N equals to side AB of the right triangle A and B over side AM of the right triangle A and N. AM is 5, AN is 2x, AB is x plus a, and AM is 5. So in total, according to equation 1, we found out that 5 over 2x equals to x plus a over 5. Here, of course, multiply this equation 1, and finally found out that 5 times 5 is 25. So 25 equals to 2x times x plus a. Here we divided this equation 1 by 2, and finally found out that 25 over 2 is 12.5, 2x over 2 is x, so in total this expression equals to x times x plus a. So according to equation 1, we shall find out that 12.5 equals to x times x plus a. Our mission is to find out the area of this rectangle ABCD. So what is the area of rectangle ABCD? Actually, we know that the area of any rectangle equals to the length of the rectangle times the width. And therefore, the area of rectangle ABCD must be equal to the length of the rectangle ABCD times the width. What is the length of this rectangle ABCD? The length is AB. And the length is AB and the width is DA. Again. The length is AB and the width is AD. AB equals to x plus a, and DA equals to x. Again, AB equals to x plus a, and AD equals to x. So in total, the area of rectangle ABCD must be equal to x plus a times x. But according to equation 1, x plus a times x is 12.5. Therefore, we can substitute x plus a times x by 12.5 here. And in total, we shall find out that the area that we are working on in this question, that is the area of rectangle ABCD, equals to 12.5 square meters. So in both methods, we shall find out that the area of this rectangle ABCD is equal to 12.5 square meters. Okay, thank you very much.